Hi, and welcome to this tutorial on Genomic SEM, and specifically a tutorial on fitting Genomic SEM models without an individual SNP effect. And today's video is on how to perform those models. We also have written a wiki page on the GitHub, right? So navigate to github.com/genomicsem/genomicsem, then click on the header wiki, and you'll find a number of tutorial pages or pages with instructions how to perform analyses in Genomic SEM. And actually the third chapter of the wiki is models without individual SNP effects. And that's what we're discussing in this video. And actually we're running the code from this tutorial, right? And what the code will do, it will first download GWAS summary data for a number of psychiatric disorders, specifically bipolar, schizophrenia, depression, PTSD, and anxiety disorder. We'll clean those summary statistics in the sense that we'll take them from their format as they're uploaded by the authors. And those formats can vary quite a bit between authors and groups, and put them into a single uniform format. This step we call munging. Then we'll take a step in which we'll compute the genetic covariance matrix using LD-score regression, and we'll compute the matrix of standard errors associated with the genetic variances and covariances as discussed in a previous video, right? We had a video about computing the matrix S, this matrix, and the matrix V, which is the covariance matrix of all the elements in the covariance matrix. Once those two steps are done, we can actually start fitting models. We'll first fit a common factor model, and then we'll manually fit a model with a common factor that loads onto schizophrenia, bipolar, MDD, PTSD, and anxiety, and add a second factor as an illustration. And basically allow you guys at home to follow along. Now, to follow along, you'll need to download GWAS summary data. And this is a neat trick. If you're on a Mac or a Linux machine, you can actually run command line scripts in a terminal in R, right? So I've written this script to download the LD scores we'll need for the LD score regression, a list of hubs, which is the list of high quality SNPs we'll use for LD score regression, and also the GWAS summary data from either the PGC website or from James Walter's group who did the CLOS UK GWAS of schizophrenia, and unzip all those GWAS summary data. Now this would take quite a while to run because it's like 3 gigabytes of data you have to pull in from the internet. I've already ran it. So that's a step we're going to assume you do yourself at home. Okay, without further ado, let's move over to the script for this video. And as a first step in this script, I'll require Genomic SEM and the package data table. And I'll require data table because one of the files has a column that's sort of not easy to work with. In its SNP column, it actually has RSID and base pair and chromosome and allele A1 and allele A2 concatenated together as one variable. And that's not what we want. We want a specific variable that's only the RSID for the SNP. And so step 0 is to prepare specifically that schizophrenia GWAS and pull out the RSIDs from that one column. And I've written a bit of code here to do that. And it will take quite a while to run, and it will heat up my computer a bit. So there we go, and I'll then have to patiently wait for this code to run before we can actually take the next step.
5 hours later.
Okay, that code has managed to run, and we've prepared the summary data for further processing. And now we are ready to munch. So the munch function takes a number of arguments. Let's look at the help page real quickly. Now we try to be good about updating the help pages, but all of us developers for Genomic SEM have an actual career on the side in which you have to do science. So they may lag behind sometimes, or they miss certain information. So basically munch is a function that processes GWAS data and prepares them for LD score regression. So we'll take in those large GWAS summary data files and it will write out smaller processed files which are ready for use in LD score regression. Okay, so the first argument is called files, and it actually just is a vector of file names which are the names of the GWAS files you're going to process, right? And the second argument is HM3, HopMap3. And it's basically, I don't know why we called it HM3. We could have called it filter or, snips or selection or whatever. But it's the argument you use to provide a list of snips you think are high quality snips or highly efficiently imputed snips. And for LD-score regression, people have commonly used those HopMap3 snips, right? Because they're well imputed, they behave well. So we trust LD-score regression analyses based on these snips will be a good reflection of the heritability or genetic correlation between traits. Okay. The next argument is a vector of names for your traits. Gotta be said, pick memorable names because you'll need those names later. There'll be the prefix for the file names. Okay, so very long strings of unintelligible things are probably not useful. Especially if you return to a project in 7 months and you've called something flip flop flip, then you won't know what it is. Whereas if you call it SCZ for schizophrenia or BIP for bipolar, you might still recall what the file was you processed. Though it's better to rely on scripts than to rely on file names. Then a vector of sample sizes, an info filter for files that, if these GWAS files have an info column, it will filter SNPs with an info below 0.9. And a minor allele frequency filter, if these files have a minor allele frequency column, it will filter SNPs with a minor allele frequency below 0.01. Now, I say if because not all GWASs come with info and MAV columns. And so you will have to work with what you got, right? And this is another reason to consider those high quality HopMap3 SNPs, because sometimes you are simply unable to filter on things like info, which reflects imputation quality, or minor allele frequency. Okay, let's run this code. I should have started running it while I was talking, but I didn't. So now we'll have to wait a bit again. And as you can see, while it's running, it will keep you up to date via the terminal, and it will also write a log file. And it usually takes a few minutes, about a minute per file, which isn't that long, but if you're fitting models with like 50 traits, it will take 50 minutes, right? So as a rule of thumb, as many minutes as you have traits. And depending on how many traits you have, you may go for a cup of coffee, you may just check your Twitter, or you may just want to, take the afternoon off and have a nice long hike.
A few minutes later.
Okay, so the munge step in LD-score regression is done. It took 12 minutes, a bit longer than I'd expected, but that's probably because I'm screen recording at the same time. And if you scroll back up a bit or look at the log file it has produced, you'll see that it tells you what it's doing. And it's munching 5 summary statistics files, time it started, names of the files, which may be important if you have a lot of file names that are similar. Make sure the right files are read in, and it will then tell you for each column in each file what it's interpreting it as. So it finds a column SNP and it says, I'm interpreting that as the SNP. In other files, it may find something like SNP ID. Well, actually, no, that's probably SNP. Makes sense for you to go through this file and check whether the things it's doing are correct, right? So important to check whether these column names are what you want them to be or are interpreted as you want them to be. Then it will start filtering. It will remove rows that are in the summary statistics file, but not in the HopMap3 SNP list, the SNPs we think are high quality SNPs I want to keep. It will then determine the effect column to either be an odds ratio or a beta. It will do this by determining the mean or the median of the column over all SNPs. If the median is around 1 or the median is around 1, it will think, well, that's an odds ratio. If the mean or the median is around 0, it will assume that that's actually a beta, right? And makes sense for you to double check whether it's doing this correctly. Okay. And so usually for a paper, You would take an hour, half an hour to go through these log files and make sure everything is done correctly. Once you've run LD-score regression, your working directory will contain sumstats.gz files, which are like 12 or 13 megabytes. They're far smaller than GWAS summary statistics because they only contain 5 columns, removing all the excess information you don't need, and they only contain 1.3 million SNPs. Now, mind you, if the overlap between your GWAS and the HuffMob SNPs is only like 150,000 SNPs, you don't want to run LD-score regression. You want to figure out why the overlap is so small. Right, so it's also one of the things the log will report to you. It's how many SNPs are deleted for what reason. Now, in this example, I'm in here. 260,000 SNPs were removed from the bipolar GWAS because the info doesn't cross the threshold of 0.6. Right, so that's the reason for exclusion. You can go back to the bipolar file and manually check whether that's true if you somehow suspect there's something amiss with your bipolar file or your analysis. For LD-score regression, you need to define some arguments. First argument is which traits we're going to use, the sample prevalences of the GWASs. Now, Andrew has been so kind at some point to check these out and look these up. And well, he had to. We were using them in the original Genomic SEM paper, and then also the associated population prevalences of these disorders. So here we're assuming schizophrenia has a 1% population prevalence, bipolar has a 1% population prevalence, and for example, MDD has a 16% population prevalence. And then you will also need to point LD-score regression to where it can actually find the LD scores, which, as we've shown before, have been downloaded from the internet. And then you define trait names. At this step, the trait names you define will be your variable names in your model later. So definitely here you want to choose memorable names. Okay, let's run this, which again will take a few minutes, but by the magic of video editing, I can omit those minutes and make the video move along rapidly. But you may want to go and have a cup of coffee.
80,000 impressions later. Would you please stop imitating me? It is starting to get very annoying.
Okay, that finished running. And if you scroll back up a bit, you can see that it will produce sort of information for you to consider, right? It will tell you, okay, the mean chi-square across the SNPs for the MDD sumstats is 1.26, lambda GC, a metric of genome-wide inflation, the LD-score intercept, which is supposed to be 1. An excess of 1 is actually a metric of population stratification in your GWAS. It will report the heritability on the observed scale, and the heritability is Z statistic. Now, it will do so for all the heritabilities and genetic covariances, right? And at the bottom, it will report genetic correlations and heritabilities. All of this is also written to a log, which you can consider at your leisure and make sure that everything's correct before you consider even publishing Genomic SEM results. Now, let's have a look at what was created by this LD-score regression function. So we're going to do some ad hoc inspection of this R object. The ldsc output is where you've stored the output of your LD-score regression, and it contains a matrix V and a matrix S. And the matrix S is actually 5 by 5, and it's a genetic covariance matrix. So let's have a look. The row names of the matrix are the variable names, and on the diagonal you'll find the heritabilities of the traits on the liability scale, because it converted the observed scale heritabilities to the liability scale using the population and the sample prevalences. You can find the details of that in Grotzinger et al. On how that does that. And on the off-diagonal elements, you'll find the covariances between these traits. Now, as Andrew has discussed in another video, and I've discussed in the other video as well, a structural equation model actually takes the covariance matrix as observed in the data and the covariance matrix implied by your model, and tries to pick the parameters for the model such that it minimizes the distance between those two covariance matrices. And that's what we're going to do right now. The first model will fit. I'm going to save this output, right? So we don't have to rerun all those slow steps again. The first model will fit is a common factor, which is basically the model you'll see here, which says that a single latent factor explains the covariance between the psychiatric disorders we're considering. Now, such a model, in some people's eyes, and I think that's a really reasonable perspective, carries a strong causal implication, namely that there is a shared cause of these traits, right? And we can get into how you can actually test whether that's a reasonable hypothesis later. Now we're just going to run the model. Okay, let's run the common factor. Now, running the model doesn't really take that long, 0.7 seconds to be exact. Now, you can imagine if you run a GWAS with 10 million SNPs, 0.7 seconds times 10 million is actually quite a bit of time. And then we'd want to parallelize it and run it on a cluster computer perhaps. But right now, for this snipless model, it doesn't matter. And so the output you get from, let me just resize the window here so we can like check the output out. From LD score regression is an object within it some model fits that you can consider to compare two models. For example, the difference in chi-squares and degrees of freedom. You can test, significance test of difference between models. If the models are not nested, you can consider the AIC to compare models. And then there is the CFI and SRMR, which are not relative metrics of two models, but absolute metrics. And I refer you to the literature or the wiki page or our articles for details on how to interpret these metrics and whether you consider something good. This will also depend on your application and many factors. I also encourage you to be strict on yourself and not just consider something good because you want the model to be good. But I can only encourage you to do so. And if you pick me as a reviewer, I will compel you to do so. So, careful what you wish for in listing me as a reviewer on your Genomic SEM article. I'm pretty sure the other Genomic SEM authors are similarly inclined. So, you'll have to deal with someone's neuroses about fit statistics. Then the other part of the model output is actually the parameters, right? So this is the loading of schizophrenia, the first factor F1. This is the value of the loading. It's a standard error, and this is the standardized loading. Standardized loading also has a standard error, and there's a p-value, a very significant parameter. If you were interested in testing the parameters, you'll get factor loadings, but you'll also get residual variances. And so residual variances are variances in the traits that are not explained by the factor, and they're on the scale of the original heritability. So 9% of the variance in bipolar disorder is not explained by the latent factor. Okay, good to know. Good, let's move on. This was a single common factor model, and we've been so kind to define a function specifically for you to use to fit a common factor model, but in many cases you may want to fit a different model, right? So to get into the habit of fitting our own models, we're going to start by defining a common factor model. Now, you should really, if you haven't watched Andrew's video on Levant syntax, you should pause now and go watch that video and then come back, because we're going to use Levant syntax and I'm going to assume you understand it because he has already explained it, right? So please do that and come back. Okay, well, if you're still here, you had watched the video already. If you're just back, welcome back. Here we define a common factor model. We define it as a latent factor F1, which is measured by, that's what this equal sign plus tilde means, measured by schizophrenia, bipolar, MDD, PTSD, and anxiety, right? So a factor causes variance in those disorders. And then we also define the factor variance to be 1. We fix it to be 1. Now, it's an identifying characteristic. We need to fix the variance of the factor to 1, or we need to fix one of the loadings on one of the indicators or disorders to 1. And let's run the common factor model using the code for usermodel. The code is actually designed to read your model, which may be different than a single factor model, and fit it to the data. And so we've already seen the fit of the model, and those of you who've seen model fits before will know that SRMR of 0.22 is pretty high and a CFI of 0.85 pretty low. So the fit of the model to the data is not great. And we can try and improve the fit to the model. Okay, so we can try and fit another model. And to determine what kind of model we should fit, we should definitely try and check out what the residual covariances are in the model. And so one of the arguments we can add to usermodel is imp_cov, and it will give us the implied covariance matrix. We'll set that argument to true, and we'll rerun the model. Now, doing so gives us the model implied covariance matrix and the difference between the model implied and the observed covariance matrix, right? Which we calculate as observed minus implied. And it will tell us where there is still covariance between traits that is not explained well by the model. And if we look at this matrix, we'll see that there's actually a slight, well, actually maybe a substantial residual correlation between MDD and anxiety, which are very similar disorders, and their covariance isn't explained by only the common factor. And so a model we could consider is a model in which we allow a residual covariance to exist between MDD and anxiety. And we'll call it common factor model 2. We'll call the output common factor self 2, right? To distinguish it from the previous model. And we can check whether this model fits the data better. Let's go. Let's run it, and let's scroll up and figure out whether there's anything in terms of model fit that improved. Well, wow. So the CFI of this model is 0.98, which is way higher than the one before, right? We can look back, it was like 0.85, and SR, MR are way lower. So that those are in the correct direction. That's what you want. The model fits the data better if we allow for a residual covariance between MDD and anxiety. So the last bit of this video went a bit chaotic, but that's what you get if you ad hoc try to fit new model. You can try and improve the model further yourself. You could consider whether there's still residual genetic correlation between schizophrenia and bipolar. Maybe you remove the genetic residual correlation between anxiety and MDD. All kinds of things you can consider. I encourage you to try. And some of those things we may introduce in the live practicals in June. Thank you for watching, and I'll catch you in the next one.